random experiments with several steps, tree diagrams. Tree diagrams can also help us to determine the probability of an event when that event has multiple steps. To create a tree diagram, we map out the possible options for the first step, then the second, and so on, until all the possible options are included. For example, let's create a tree diagram to map out the options of flipping a coin 3 times. Step 1. We list out the options, which in this case are just heads or tails. Then step 2. Follow each of the results in the first step, and again list all the possible options for the second step. In this case, because we're just flipping a coin, it will be heads and tails again. And so on for step 3, we repeat that process. And we continue adding steps for as long as necessary to complete the tree. Let's take a look at what that looks like. So you can see on the first flip of the coin, we had 2 possible outcomes, heads or tails. Now regardless of which one came up, there were 2 possible options on the next flip, again heads and tails. Similarly, for each of those outcomes, again heads and tails outcomes. And that completes the tree based on flipping a coin 3 times. We can then add probabilities to each step in order to determine the probability of any particular outcome. The probability of any outcome is the product of each result needed to obtain that outcome. So the probability of an outcome A, B, C is equal to the probability of A times the probability of B times the probability of C. Going back to our coin flipping example, this could be expressed as the probability of getting tails, heads, tails, or any of the other possible combinations that we were discussing, which in that example, the probability of getting either one of those at any time, so the probability of getting tails and the same as the probability of getting heads, is 1 out of 2. So the probability of getting tails, heads, tails is 1/2 times 1/2 times 1/2, which is equal to 1 out of 2 times 2 is 4 times 2 is 8. And if we go back to our tree on the previous page, we're looking for the path as tails, heads, tails, and you can see that there's only one path that gives us that, and there were 8 possible outcomes. So the probability of tails, heads, tails was 1 out of 8. Keep in mind that in this case, the probability of heads is the same as the probability for tails, but that isn't always going to be the case. So this fills out the full table, showing you that the probability of getting any particular outcome, because flipping the coin heads or tails is exactly the same probability, 1 out of 2, that every probability that you end up with is always 1 over 8, or 1 out of 8. Independent events are events in which the occurrence of one event doesn't influence the probability of the other event happening. For example, so if I flip a coin and I get tails, when I'm about to flip the second coin, the fact that I got tails doesn't have any influence on what I'm going to get the second time I flip the coin. That's an example of independent events. Let's investigate an example. You're drawing marbles from a bag that contains 3 green marbles and 2 blue marbles. After you draw each marble, you'll put it back in the bag. If you draw 3 marbles, what is the probability of drawing a green marble on the first draw, followed by a blue marble, followed by another green marble? In other words, that's the probability of green, blue, green. Let's take a look at that. On the first draw from the bag, we can have a choice of getting either a green or a blue. The same on the second draw, there's either green or blue. And the same on the third draw, green or blue. The probability of getting green on the first draw, because there are 3 green marbles and 2 blue marbles, that means there are 3 possibilities out of 5 that will get green. Conversely, for the blue, the probability of blue, because there are 2 blue marbles out of a total of 5, the probability is 2 out of 5. Now, because we put the marbles back into the bag for the second draw, we still have the same probabilities for getting green and blue. Probability of green on the second draw is still 3 out of 5, and the probability for blue is still 2 out of 5. And the same on the third draw, the probabilities are going to remain the same. Now let's follow through and look at the outcomes for each of these series of draws. So going across the top, we have a green, green, green outcome. The next one down will be green, green, blue. Going to the next branch below would be green, blue, green, followed by green, blue, blue. Then we go down to the, starting with blue branch, blue, green, green, blue, green, blue, 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 green, and blue, blue, blue. Now let's look at the probabilities of each of those occurring. So the probability of getting green, 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 we take the product of each of the probabilities along that branch in the tree. So we have 3 over 5 times 3 over 5 times 3 over 5, which is equal to 27 over 125. Now let's look at the probability of green, green, blue. This time we've got a probability of 3 out of 5, another 3 out of 5, but then the probability of blue is 2 out of 5. So in this case, it's 3 out of 5 times 3 out of 5 times 2 out of 5, which is equal to 18 out of 125 this time. We'll do one more. The probability of green, blue, green. So it's the probability of green, blue, green, which is 3 out of 5 times 2 out of 5 times 3 out of 5 again, which is the same as the one above, which is 18 out of 125. And we continue that process down through the rest of the calculations for each of the branches in the tree. Now going back to our initial question of what's the probability of green, blue, green, if we follow through that path in the tree, green, blue, green, the probability is 18 out of 125. Dependent events are events where the occurrence of one event does change the probability of the other event happening. The best example that we can use for this case is when you're drawing the marbles out of the bag. If you didn't put the marbles back into the bag, your probability of choosing each color changes depending on which marbles you've taken out. Let's see how that works in an example. You're drawing marbles from a bag that contains 3 green marbles and 2 blue marbles again. After you draw each marble, you don't put it back in the bag. If you draw 3 marbles, what is the probability of drawing a green marble on the first draw, followed by a blue marble, followed by a green marble again? So that is, we're looking for the probability of green, blue, green again. So let's start with that. So on the first draw, the probability of drawing green, because there are 3 green and only 2 blue, we have a probability of 3 out of 5. Similarly, the probability of drawing blue is equal to 2 out of 5. However, now when we get to the next draw, because we didn't put the marbles back into the bag, if we drew a green marble out of the bag and kept it out, the probability now of drawing a green marble the next time is only 2 out of 4. Because there are 4 marbles left in the bag, we've taken one of the green ones out, so we're down to just 2 green marbles. Similarly, the probability of drawing a blue marble is 2 out of 4 because we haven't taken any of the marbles out and there are 2 blue marbles. Now looking at the third draw, if we drew a green marble on the first and second draws, then on the third draw we have fewer marbles to draw from in total and we have fewer green to draw from. So the probability of drawing green on that third draw, we only have 1 green marble left out of a total of 3 marbles that are in the bag. So the probability is 1 out of 3. The probability of blue, in that case, is equal to 2 out of 3, because we haven't drawn any of the blue marbles out yet, and there were 2 to start with, and there are a total of 3 remaining. We can follow through the rest of the branch now as well. So if we drew a green marble on the first draw and a blue marble on the second draw, then the probability of getting a green marble on the third draw, we've taken 1 green marble out, so we know there are 2 green marbles in total. We've taken 1 blue marble out, so we went from 5 to 4 to 3 marbles left in the bag. So the probability of getting green is 2 out of 3. Similarly, the probability of getting blue, since we've taken 1 blue out, there's only 1 blue remaining, and there are 3 marbles in total in the bag. we can go ahead and complete the rest of the tree. There are a couple of things to note in the tree. Notice how 3 and 2 add up to 5. And this holds true whenever you've got 2 and 2, they add up to give us 4. In the final stage, we've got 1 and 2, they add up to give us 3. So you can always double check to make sure that you've got everything on track just by checking those numbers. It's also worth noting, we ended up with a 0 in the last space. And that makes sense if you think about it. In the first draw, we drew a blue marble, and we left it out of the bag. In the second draw, we also drew a blue marble and left it out of the bag. Since there were only 2 blue marbles to start with, we've taken both of them out. There's no chance that you're going to get another blue marble because there are no more left in the bag. So let's go back to our initial question here of the probability of getting green, blue, green when we're not putting the marbles back into the bag. So that's following this branch of the tree. We can calculate the total probability by calculating the probability for each draw. So the probability of green the first time is 3 out of 5. The probability of blue the second time is 2 out of 4. And the probability of getting green on the third draw is 2 out of 3. We multiply that together and we get 12 out of 60, which we can reduce down to 1 out of 5, because each of them is divisible by 12. If we had other probabilities we needed to calculate, we could go ahead and calculate the outcome for each one of the branches in the tree. Add this to your memory aid. Try the practice questions in the workbook and check your answers against the answer key.